Next question. A wave function for a particle in a box is sketched below. What is the value of the quantum number? So we have given a wave function here. We want to say what will be the value of n for this wave function to be in this form. So option A is 1, option B 2, option C 3, and option D 4. So when we study the quantum mechanics, when we are plotting the wave function, we can easily calculate the number of nodes of this number of the nodes of each wave function. So the number of nodes, if we are plotting a wave function, is equal to n minus 1. So when we are drawing the wave function of n equal to 2, the number of nodes will be n 2 minus 1, that will be 1. Here, when we count in this graph, we can say that there is 2 points in this graph where the probability of finding the electron is 0. That is, number of nodes in this graph is 2. That is 1 here and 1 here. So in this graph, the number of nodes is 2. So according to the equation, the number of nodes is equal to n minus 1. So this will be the graph of n equal to 3, because only when n value equal to 3, the number of nodes will be 2. That is 3 minus 1 equal to 2. So the correct answer will be C, that is 3. This graph is of the this wave function. This graph will be the wave function of a particle with a quantum number equal to 3. Here n value will be 3. So the correct option will be option C, 3.
So given below are two statements. One is labeled as assertion and other is labeled as reason. Assertion, as what is assertion statement? The density of diamond is much higher than that of ice, though both solids adopt analogous structure. Reason, the ice lattice is held by hydrogen bonds which are significantly weaker than the covalent CC bonds in diamond. So when we see the structure of both diamond and ice, both have cage-like structures, but in diamond, it is formed by carbon-carbon covalent bond, which is very strengthened than the hydrogen bonds between two water molecules. So in water molecule, hydrogen bonds between two neighboring water molecule will form an open cage-like structure, and that is the reason because of the open spaces in ice, it is very less dense. So these both statements are true, and reason is the correct explanation of the assertion. So the option A is true. Both assertion and reason are true, and reason is the correct explanation of assertion, because even though both adopt these analogous structures, ice is very less dense compared to that of diamond, because in ice there is a vast hydrogen bond between the water molecules. So it will form open cage-like structure which gives spaces between the molecules. And next question. It is from nuclear chemistry, but it can be easily solved. Considering the following reaction, that is uranium-238 is plus helium atom gives a atom, that is X, with a mass number M and atomic number A, and one neutron is displaced from this reaction. We want to predict the number of neutron present in the nucleus of X. So option A is 147, B 238, C 94, and D 162. We want to say what is the right answer. So here we can see in the reaction side, two atoms are combining, that is uranium and helium. So uranium-238 and helium. So the mass of uranium is 238 and helium is 4. So here we can see in the product side, one neutron is removed. Neutron also have a mass of 1. So if we want to find the mass of the atom X, we want mass number of the atom X, we want to do this calculation, that is 238 plus 4, that is the mass of the reactants, minus the mass of the neutron, minus 1. So we will get the answer as 241. And when we see the atomic number, we can see uranium 92 and helium 2 is combining, and in the reactant side, neutron have 0 mass. So we just want to add these two atomic number. Neutron have no atomic number, that is have no charge. So we want to just add the atomic number of uranium and helium, that will be 92 plus 2. So 92 plus 2. So the atomic number of X will be 94. So we are asked to find the number of neutron. If we want to find the number of neutron, we have to minus the mass number. We want to minus the atomic number from the mass number. Only that will give us the number of neutrons. So when we do the calculation, number of neutrons is equal to 241 minus 94, that is 147. So our correct answer will be option A, 147. Next question. A commercial FM radio station operates at 100 megahertz. The wavelength lambda of the radio wave is dash. Given C is equal to 3 into 10 raised to 8 meter per second. So they have given the frequency. We just have to find the wavelength. Option A, 3 into 10 raised to 12 meter. B, 3 meter. C, 3 nanometer. And D, 300 nanometer. So it is just an equation. We just want to know the relation between the frequency and lambda. So mu frequency is equal to C by lambda. So here lambda is given as C is given as 3 into 10 raised to 8 and the frequency is given as 100 megahertz. So if we want to find lambda, lambda is equal to C by mu, and mu that is frequency is 100 megahertz. So 1 megahertz is equal to 10 raised to 6 hertz. We want to convert that also. So when we are doing this, lambda is equal to C by mu. C is equal to 3 into 10 raised to 8 divided by 100 into 10 raised to 6. We will get lambda. That is the wavelength of this wave in the FM radio as 3 meters. So our correct option will be option B, 3 meter. Next question. For the following electrochemical cell, Cu solid is oxidized to Cu2 plus and it is separated by a salt bridge, and the Zn2 plus ion is reduced to Zn metal. So choose the correct option in the light of the following standard electrode potential. So here in the electrode potential of the two half cells are given here. First, copper is reduced to copper and it have an electrode potential of plus 0.34, and Zn2 plus is also reduced to Zn and it have a reduction potential of minus 0.76, and we have to predict the potential of the cell and what will be the nature of the zinc electrolyte. So option A, the potential of the cell is minus 1.10 volt and the zinc electrode is negative. And option B, the potential of the cell is plus 1.10 volt and the zinc electrode is negative. And option C, the potential of the cell is minus 1.10 volt and the zinc electrode is positive. And D, the potential of the cell is plus 1.10 volt and the zinc electrode is positive. So we can see this question, answer this question. So here from the cell equation, we can say that in the left hand portion there will always be anode half cell. So here copper is converted to Cu2 plus, so that is anode half cell, and the Zn converted to reduced to Zn, that will be the cathode half cell. So in this table it is given as the reduction potential of the copper, but here copper is getting oxidized. So the reduction potential of copper is given, that is plus 0.34. So the negative of the reduction potential will be the oxidation potential of the copper. So oxidation potential will be minus 0.34. In this reaction, copper is getting oxidized. So we should consider the oxidation potential of the copper, not the reduction potential. So it will be the negative of the reduction potential given here. So it will be minus 0.34. So if we want to find the E0 of a cell can be calculated by this equation, that is E oxidation potential of anode plus E reduction potential of cathode. So when we do the substitution here the E oxidation potential of anode is minus 0.34 and the E reduction potential of the cathode is minus 0.76, and when we add this we will get it, the E0 of cell as minus 1.10 volt. So the potential of the cell will be minus 1.10 volt. And we know that here the zinc is a cathode. In electrochemical cell, cathode will be always positive and the anode will be always negative. So here the correct option will be option C, not D. That is a correction here. Option C will be the correct answer because the potential of the cell when from calculated value we got it as minus 1.10 volt and zinc electrode is cathode here, so it will be positive. So option C, the potential of the cell is minus 1.10 volt and zinc electrode is positive will be the correct answer. Next question. If delta H0 vaporization, that is enthalpy of vaporization is 30.8 kilojoule per mole and enthalpy and entropy is 87.2 joule per mole per Kelvin for benzene. What is the boiling point of the benzene? Assume that enthalpy of vaporization are independent of temperature and delta S are independent of temperature. We want to predict what will be the boiling point of benzene from the two values given here, that is enthalpy and entropy at that particular temperature. So the options given us 0.35 degrees Celsius, B 353 degrees Celsius, and C 80 degrees Celsius, and D 1 degree Celsius. So from equation, we can say that temperature is equal to delta H0 vaporization, that is enthalpy of vaporization divided by entropy of vaporization. If we want to find the boiling point, we just have to do this equation, that is delta enthalpy divided by entropy of vaporization will give us the boiling point of any substance. So when we do the substitution, that is enthalpy of vaporization is given as 30.8 kilojoule, that is 30.8 into 10 raised to 3. So 30.8 into 1000 divided by delta enthalpy of entropy of vaporization is 87.2. So when we divide that value with 87.2, we will get it as 353 Kelvin. So here we can see all these values are in Kelvin inverse. The entropy is in Kelvin inverse. So when we do this equation, we will get the temperature in Kelvin. But in the options, it is given temperature in degrees Celsius. So we want to convert the Kelvin temperature into degrees Celsius. So 353 minus 273 will give 8 degrees Celsius. That will be the correct answer. So our answer will be C, 80 degrees Celsius. Next question. The phosphorescence wavelength is. So it is a direct theory question. We want to predict what will be the nature of the wavelength of phosphorescence. Option A, longer than the absorption wavelength. B, equal to the absorption wavelength. C, shorter than the absorption wavelength. D, equal to fluorescence wavelength. So here we can see from the S0 state, the electron or any particle is excited to S1 excited state as a singlet one state, and after the intersystem crossing, it is gone to the triplet state. And here we can see from the triplet state, this radiation is emitted by the particle to reach the S0 state. That process, the energy absorbed by the particle is emitted as phosphorescence. Here we know that a lot of energy is absorbed by the particle to move from S0 to S1 after vibrational relaxation and after intersystem crossing. There is a great loss of energy by the particle. It reaches the triplet state, and at that triplet state also the particle is undergoing vibrational relaxation, and after that it reaches the S1 or S1 state. So a lot of energy is lost by the particle for phosphorescence to happen. So always phosphorescence will have lower energy. That is, lower energy means it will have a longer wavelength. That is, energy is inversely proportional to wavelength. So if a particle have a lower energy, it will have a longer wavelength. So the phosphorescence wavelength will always be longer than the absorption wavelength because of the loss of energy in processes like vibrational relaxation and intersystem crossing. And at the end of this process, phosphorescence will happen, and so the wavelength of phosphorescence will be always less than that of the absorption wavelength. Next question, which of the following statement is false? Option A, it is related to the IR and Raman spectroscopy. So option A, there are 4 vibrational modes in carbon dioxide. Option B, the IR spectrum of carbon dioxide shows only 2 absorption bands. C, IR active vibration bands must have a change in dipole moment. And option D, the bending mode of CO2 is IR inactive. We can see. So in carbon dioxide, we can say there are 4 modes of vibration. That is symmetrical stretching, asymmetrical stretching, and 2 bending vibrations also is present here. So this is equilibrium structure, symmetrical structure, asymmetrical stretching, and 2 bending vibrations. Scissoring and rocking is also present here. So here we can say that there are 4 modes of vibration. That is the true statement. So option A is not the correct answer. We want to find the false statement. And in the IR spectrum of carbon dioxide shows only 2 absorption band. That is also true. That is 2 bending vibrations of carbon dioxide will give 1 band and 1 stretching. That is symmetrical stretching is not IR active because there is no change in dipole moment after symmetrical stretching. So it is not IR active, but asymmetrical stretching is IR active. So it will also give 1 absorption band. So 1 absorption band will be given by the asymmetrical stretching and 1 absorption band will be given by the bending modes of vibration. So we will get 2 absorption bands. That is also true. And option C, we can see IR active vibration bands must have a change in dipole moment. That is also true. For a molecule to be IR active, it should have a change in dipole moment. If there is no change, that molecule will not be IR active. And option D, we can see the bending mode of CO2 is IR inactive. That is not true. The 2 bending modes are given here. Both are IR active. So the fourth statement, that is bending mode of carbon dioxide is IR inactive, is a wrong answer. So our correct answer here, we want to find the false statement. The false statement is option D. The bending mode of carbon dioxide is IR inactive. Next question. Given below are 2 statements. Statement 1, every molecule has a vibrational Raman spectrum. Statement 2, in vibrational Raman spectra, Stokes lines are more intense than anti-Stokes lines. And in the light of the above statement, choose the correct answer from the options given below. Option A, both statement 1 and 2 are true. And B, option both statement 1 and 2 are false. And C, statement 1 is true but statement 2 is false. And option D, statement 1 is false and statement 2 is true. So when we see the Raman spectrum, the Raman spectrum is based on the change in the polarization of molecule. All molecules are Raman active. That is because when it interact with a radiation of a particular wavelength, it can easily undergo, that molecule can easily undergo polarization. Any molecule can undergo polarization. So every molecule is vibrational, has vibrational Raman spectrum. That statement is true because there can have an unequal charge distribution and all molecules will be Raman active. And statement 2, in vibrational Raman spectra, Stokes lines are more intense than the anti-Stokes lines. Here we can see in the Raman spectra, there are 3 cases, Stokes shift, Rayleigh scattering, and anti-Stokes shift. So when the energy absorbed is equal to the frequency absorbed is equal to the frequency emitted, we call it as Rayleigh scattering. And when the frequency absorbed is greater than the frequency emitted, we will call it as Stokes shift. And when the frequency absorbed is less than compared to that of the frequency emitted, we will call it as anti-Stokes shift. So, and the intensity is also drawn here. Rayleigh scattering will be the most intense one, and after Rayleigh scattering, Stokes scattering will be the most intense one, and anti-Stokes will be the less intense. So in this second statement, it says as in vibrational Raman spectra, Stokes line is more intense than anti-Stokes line. That statement is also true. So our correct answer will be option A, that both statement 1 and statement 2 are true.